You didn't get their names. David?
Lazaro. Ricky.
Yeah. And yeah, they're on one of the teams. We currently have 4, maybe 5, who knows? Don't completely know because some of these registrations are not working out, but we'll figure that out. Okay. Oh, what did I do? Sorry. I think I turned it off. Okay, maybe I'll just use the board and explain a few things first while this thing gets. All right. So let's spend 15 minutes on range trees, and then we will talk about competition and preparing and so on. Yeah? Okay, good. So first thing is, what is a range search problem? It's still cooling down, and I don't want it to cool down.
Yeah. It always takes so long.
Sorry.
Okay.
All right, so first of all, you all know what a search tree is. What's a search tree? Let's start with something simple. Search tree, an example is a binary search tree. What does that do for you? What's it good for? It helps you to search values because it organizes things in some smart way, where at any given node, the smaller things are on the left side and the larger things are on the right side, and so on. So it helps you to do search. It is a sublinear search only if it is balanced. So until then, you can't quite say that, right? So a search tree is a general structure that helps you to do search for values because it organizes things nicely. So that brings us to a binary search tree where it's basically a search tree, but you have binary. And then you have something called a balanced binary search tree, which has this nice property that the height of the tree is small, right? So these are structures you guys learned long ago, very straightforward stuff. And an example of a balanced binary search tree is your well-known red-black tree, which I'm hoping you've seen in your class somewhere, right? Whether you've seen it or not, for sure it should be a piece of code that you should take with you for the competition, because you're going to need it anywhere and everywhere, who knows. Now we know that we can search for items quickly in these red-black trees in essentially log n time, because the heights are oh, system off. How did I do that? So that brings us to the next question. We want to ask what are called as range questions. Now what are range questions? I could ask, if I gave you a value x, tell me, don't just tell me if it's there or not, but find me the nearest one in your set. Okay? So it's almost like binary search, except that you're asking for a little bit more. Or you could say, give me all the values between 3 and 9 that's in this set. So again, you have to go through this tree in some smart manner and pull this out. Or I could ask simpler questions like, tell me how many items there are between 100 and 200. You don't have to go and pick out each one of these, just give me a count. Okay? Or you could say, supposing I have a class of students and each of you has, let's say your names start with certain alphabets. You have a J and an L and a D and an R. And I want to know who has the highest GPA between letters P and Z. So that's a range question, okay? Because I'm looking at a range of students and I'm asking some question. I'm asking for some search questions. These are all range queries, and they all have the same general nice structure that helps you to do interesting things. Okay, now let me make sure I don't hit anything. Source select laptop. Good. Okay. So yeah, no. So these are all the range search questions I just mentioned. If I gave you a number X, tell me what's the closest you have in the set. Return all the values between x1 and x2, or just count how many are between x1 and x2, or if there is some associated value, find me the best one, right? Or instead of actual values, I give you a range and I say, find me the count of how many are between x plus r and x minus r. All right, so as I said, these are all range trees. All of these involve working with binary search trees, but it's not that straightforward. It's not like you can just plug in a binary search tree and hope that it works out, okay? So you have to, so here's an example of a binary search tree. It doesn't look like your nice tree. It's stolen from a book, but it's up there on top of the tree. Think of that as containing the entire set. In this case, everything between x1 and x8. And then you break this down into two parts. If it's a nice balanced tree, you would have 4 items on either side. And then, so actually this is a range tree where that corresponds to a range of x1 through x8. This corresponds to x1 through x4 and x5 through x8, and so on and so forth. So it's your standard binary tree structure drawn in some strange way. And as you can see, these are your leaves. They correspond to individual values somewhere in the tree. And because they're in increasing order, your leaves are also going to be in increasing order. So this is a regular binary search tree. Now, if I ask you range questions, it turns out that you can do this in this tree if you add some extra information in the tree. And I think we may have talked about this at some point. If for each node in the tree, if you add the size of the subtree, then you can do magic stuff. You can count how many things are in that subtree without actually visiting each node in that tree. And you can also do range questions now in that tree if you have this size information. And so if I want everything between x2 and x6, right, then I can do this by doing some smart stuff. And I'll show you a better picture because it's not that easily seen here. Here's a better picture. So this is your binary search tree. And I want to know how many things are between x1 and x2. And I haven't drawn the entire tree. It's there. But you're going left, right, somewhere all over the place. And your x split is the last node that has both x1 and x2 as within its subtree. All right? So if you can so you start from the top. Imagine that you're looking for x1 and x2 simultaneously. Come down, and at some point, x1 is going to be on one side and x2 is going to be on the other side. If you see this picture, then you can pretty much see that roughly speaking, the number of items, all the items between x1 and x2 are in this subtree, this subtree, this subtree, this one, this one, this one, and this one. Those are the guys that are going to be in between x1 and x2. There are a few other things that are on this path, but you can figure that out. Okay? And it turns out it's possible to count this, keep track of it, do whatever it is that you need to do. So now, if I can count these guys without actually going and visiting those subtrees, they may be very large, by the way. If I only have a count, I can quickly do this without getting into each of these trees and digging in. So essentially, it's like doing a binary search for x1 and then doing a binary search for x2. So by doing 2 binary searches, I can figure out count information magically. It's a bit of work, but it can be done. And again, you don't need to know exactly how to do this. If you have the code for it, you could manage this. So this is a standard range search problem or range query problem. You're given a range, and you're asked how many items are here. Good? So this is called a one-dimensional range query because everything is in 1D. You just have a set of values. Yeah, you can read all this stuff. It's basically what I just told you. All right, there's even some pseudocode. You're welcome to play with it if you want. And just quickly about time complexity, it turns out all the problems we mentioned can be solved in log n time, except for the problem where you have to actually print out the values between x1 and x2. If you have to go and individually pick those items, there's going to be an extra k, where k is, it depends on how many items I have to output, right? Okay, so that's how one-dimensional range query works. We're going to ramp this up and make it harder for ourselves because we are just gluttons for punishment. And so we go to 2D now. And what's a 2D range query? Well, it turns out this is pretty standard. So instead of a one-dimensional question where I'm asking, tell me all the keys between x1 and x2, I'm going to ask, tell me all the keys between x1 and x2 and y1 and y2. So remember, these are two-dimensional things. So it's like asking, give me all the names between P and R and whose age groups are in the range 20 through 25. Okay?
First it was a line segment, now it's an area.
Now it's an area, that's right. So now your points are all in 2D space. And you're asking, give me a range in x and in y, and tell me how many points there are. Right? That's what you're asking. Whereas in the previous case, all your values were sitting on a line, and you're asking how many points are between x1 and x2. Right? So the range was one-dimensional. Here the range is two-dimensional. Right? And it turns out the tricks are not that much different, but there's one important trick, and I'll show you what that is. This is the same picture I drew. I should have just shown you this. So if I gave you an x range and a y range, and I'm asking how many items are there, or tell me all the items that are there. Of course, you have to understand that the assumption is that the number of items is very, very large, right? Imagine that you have 50,000 students from FIU, and I want to know all the people whose age is between 20 and 25, and I don't know, something else. GPAs are between 3.4 and 3.5. So it's a large number. I don't want to go and visit every student and figure this out. I want to process this. I want to pre-process the data, build a nice tree structure, and then quickly answer questions, right? That's the setup. So, and the other thing that's important is that whatever I just told you also works for dynamic data sets, which means I can insert and delete things and still be able to answer the questions. We do a lot of things if my data set never changes. But if my data set is constantly changing, I'm going to need a binary search tree that can dynamically insert and delete and then answer these queries. So here is the basic idea for the 2D range tree. What I'm going to do is I'm going to build the standard range tree for the x values, the x coordinates. So imagine that every data point has an x coordinate and a y coordinate, right? So I build the standard range tree or the binary search tree for the x coordinates. Now I'm going to ask you the question, tell me all the people, all the values that are in this x range and also in some y range. And you're going, how am I going to do this? I'd have to go and look at everything because the x values and the y values have no connection to each other, right? If you look over here, the x values and y values are scattered all over the place. So even though I take the x values between here and here, it's going to have a whole bunch of other things that fall outside the y range that I want. So here's what you do. You take all the points that are in this subtree. Remember, every node in this binary search tree corresponds to a subtree. Subtree corresponds to a set of points that are in a range. And the range is everything between this value and this value, right? So every node defines a range of x values. I'm going to take this entire set, and in parallel, I'm also going to build a y data structure. So I'm going to build an extra binary search tree for their y coordinates. So now, at every node, I have this strange y structure that's going to be hanging off of it. This is called a 2D range tree. Now, how do I do the query that I really want? What's the query I want? I have an x range and a y range. Sorry, x range and a y range, right? So I first find the x range. Imagine that there's only one node that defines it. It's easy that way, easier to think about it that way. So this node here defines an x range. And then I go to its y tree. And whatever y coordinates you tell me, I'll look up the appropriate y coordinates there and work off of those points. And remember, all the points here are in the right x range. Now, some points are going to be in many, many such trees, but that's OK. All right, so this is going to be a large tree with lots and lots of information, but it's going to be so well organized that any range query you have will come out like that. Does that make sense? So by the way, I haven't looked at the video you sent me, so I don't know how they explain this, but this is how I understand it. So now you can see how this goes. I'm going to start with the x tree and find for every subtree here, I'm going to have an associated y tree. And within there, I will look at the appropriate y range and report that. And I have to do this for every node that's relevant for my search. Remember the first x range that we talked about? We have to start at the split node and then go all the way down, and then everything in between is relevant. For each one of those, I'm going to do this work now. Okay? And so it will sort of end up looking like this. If this is your split node, then every node here has an appropriate y structure where you would have to go and search. And if you do this properly, since you will see that you will count things correctly. It's a little bit of work, but that's the basic idea. Does this make sense? Yeah? Pictorially, this is what it looks like. I have that x tree. Every subtree corresponds to a range. Within here, I am interested in, so for that node, I'll go to its appropriate y tree, and I'll focus on a certain y range, and that'll give me all these points that are in this strip. Cool? Okay. So yeah, so the basic idea is first you do the x constraints, then go to the y tree, and then apply the y constraints and find the nodes that you want. And so the complexity turns out that you have to do log n work on the x tree. And then for each node in the x tree, I have to do log n work on the y tree. So it becomes log squared n. And it says n log squared n because if I have n items to store in the tree, just to construct the tree, it'll take me n log squared n. OK? Now, there are various tricks to actually make this n log n, but we won't go there. There are these fancy structures called fractional cascading and so on and so forth. So yeah, you don't want to know all this. If somebody gives you code, you're welcome to use it. It doesn't necessarily work any faster than your regular n log squared n algorithm. The amount of space that's used turns out to be still n log n, so it's actually quite great. So that gives you, well, no, there's no point in looking at this. I think really you want to look at this. It tells you what's the space and the time that it takes to first construct the tree and second to answer queries. Okay? For binary search trees, it takes n log n to construct the tree and log n to answer queries, right? It's very similar for 2D. Now, I haven't quite told you what happens in 3D, which is where we are going next. Any questions so far? Okay, great. So why do we have to go to 3D? Well, that's because David gave us this problem to look at called what? Occupation cost, right?
No, opportunity.
Opportunity cost, sorry.
We're trying to do it in an n-squared solution.
Yeah.
At first.
Yeah, let me show you the problem. So somehow my browser crashed and I'm having some trouble, so you'll have to bear with me. Crap, where did that go? Yeah. Opportunity cost. Okay, let's hope it pulls it up. Here you go. Oh. How do I get there?
It'll be at the top.
Yeah?
The problem description. Now.
Okay. All right, good. So I am going to give you a few minutes to read this up, or we'll let David explain to us what the problem is, since he's punishing us with this. Just kidding.
So, as with most types of products, finding these functions is difficult. One of the main challenges is that there are a lot of different aspects of a phone that you might care about. Its price, performance, and how user-friendly the phone is. Typically, there is no one phone that is simultaneously the best at all these things. The cheapest phone, the most powerful, the most user-friendly will likely be different phones. Thus, when we
So you're trying to buy a phone that has three properties. One is price, one is performance, and one is user-friendliness. And this says if you choose a phone, there's something called the opportunity cost, which is defined in this strange way, that you find the maximum over all the phones in the market of the difference between the price, the friendliness, and the, what was the third one? Performance. You add these things up, that's the opportunity cost, which is basically saying how badly did you do in terms of your purchase, right? Something like that. So if your phone is better in terms of price, in terms of performance, and in terms of user friendliness than all the other phones, then opportunity cost is 0. That's how this is defined, right? So you want to know what is the cost, what is the price you paid for missing an opportunity, something like that, right? So we need to stare at this definition and make sure that we understand this. This is a weird definition.
So each phone, right, you want to compare its opportunity cost. So you get it by, so the X without the I, that is the current phone you're on.
That's right.
The XI is
This is what you paid. This is what the ith phone costs,
yeah,
or price is. Here, this is the performance difference, and this is the user friendliness difference. But there's also this max with 0. What does that mean? It means that if it's negative, we'll just count it as 0, right? Yeah, you didn't miss out. That's right. So We won't have any negative numbers here, but then we're doing a max at the end where we are doing the max over all possible phones in the market. I say this definition is really weird, but okay, we'll go with it. If we only had to look at price, what do we have to do? So, well, let's say we forget all this, right? We only have price. So we want to figure out which one has the minimum opportunity cost, right? Which phone has the minimum opportunity cost? Which one do you think, if you only had price, which one would have the minimum opportunity cost?
The one with the max price.
With the best price, yeah, right? Because if it's the best price, all others are going to be lower, and you would not have lost any opportunity. Clear, great. Now let's go to two things. Let's try price and performance. If you had one phone that's better than everything in terms of price and performance, there's no question you're just going to go and that's the one that's going to have the least opportunity cost, right? If not, how does this happen? How does this work? So you can see that this is now a 2D problem, right? So we're going to do 2D picture and try and understand this. So one of the axes is, wow. One of the axes is price and the other is performance. So let's call this price and this is the performance, right? Here is some phone and you want to know what is the opportunity cost for all the other phones in the market. Or rather, actually, you want to know what's the opportunity cost of any phone in the market. So let's look at the opportunity cost of this phone in the market. Now, what I'm going to do is draw these two horizontal and a vertical line. Gives me 4 quadrants. Now, what about the things over here? What's the opportunity cost of things over here? They're worse in price, they're worse in performance. So therefore, opportunity cost is 0, right? Is that clear?
Why are we minimizing the price?
Well, we're not minimizing it. That's what they want us to do. Don't ask me why.
So this is basically
You want to say what's the best deal you can get. Really.
minimize all of that.
You want to minimize this entire quantity.
Yeah.
Right. So you want to minimize the phone, which if it were X, Y, and Z, it would achieve the smallest value. Okay? So if there is a clear one that's best in all categories, then no arguments. The problem is that's not going to be the case most of the times. All right? So how do we now work this out? That's the question. All right, so this here has an opportunity cost of 0. No problem. What about things here? Sorry? Anywhere here. So let's say we have that. So here it's clearly greater than 0, but how much is that opportunity cost?
The difference between the price and performance.
So it's basically this length plus this length, right? And this is called the Manhattan distance in some terminology. Basically, you're taking the difference in X and the difference in Y, right? Now, it turns out, so among all the things here, the one that's, well, if there is anything here, then this guy is not going to be the minimum. It's pretty clear. So you want something where this part is empty, right? So here, the opportunity cost is well, not only that, the opportunity cost of this guy is going to be better than this guy for sure, right? Because here, the opportunity cost is positive, whereas for this guy, the opportunity cost because of this guy is definitely 0. So therefore, there's no point in even considering this. You might as well just go with that. Okay? The problem is that just because you found this doesn't mean this is the winner, because there might be things that are in the other places. What about something here or something there? What are the opportunity costs for these guys? That's the question. right? This is where there are some tricky things going on. Yeah.
One is 0 and the other is non-zero?
Actually, no, that's not true. So let's apply the definition. So the way you apply the definition is that if you're comparing it with this guy, the x is smaller, so therefore the x is not going to contribute anything, right? So it's the same as sort of pushing this over here, but the y is going to contribute something. So the opportunity cost is actually that for this guy. Here, let me use a different color. And for this guy here, the opportunity cost turns out to be that one.
Yeah, that's what I meant.
Sorry, or that's, I should really have put it over here. And you don't know which one is going to give you which one is going to be higher in value. Okay? But both of these are giving you positive values. However, if I were to figure out what is the opportunity cost of this with respect to that, well, this time it's going to be that value, not this value, right? So it's not it's not symmetric. So there may be phones for which the opportunity cost on both sides are non-zero, but one is better than the other. Does that make sense? So that's where the problem is. And now, how do we turn this into a range tree problem? That's where the trick is. So it's going to take me a few minutes to explain this. Any questions so far? Is this clear? And I haven't even gotten to 3D because it's kind of nasty looking, but once you get the idea, it's quite easy. Any questions so far? So here's what I'm going to do. I'm going to take, again, I'm only dealing with two coordinates, performance and price. Okay? I'm going to build a range tree. The range tree I'm going to use in the following manner. If you give me any x, if you give me any phone, I'm going to ask, is this part empty? Because I can ask for the number of points whose x value is bigger than this guy's x and whose y value is bigger than that. That's easy for me to check in that range tree, right? So I will figure that out. If this is not empty, I'll say forget it. This guy is not even a competitor. Okay? Because I need one that's going to be better than this. All right? Is this clear? So forget about anything where this part is non-empty. So we need this to be empty. Okay? Need. If it's not, then we skip this and move on to the next item. So we're going to do for every item, we're going to go and look at this region. If it's not empty, we'll ignore it. Otherwise, we'll keep it aside. Okay? And we know we can do this in the range tree in log n time.
So we couldn't. Okay, so just two dimensions, right? Couldn't we just compare between 2 points, which is the one
Right.
that has
So
the
right. I should have started there. You're absolutely right. So here is the naive solution. I can do this for every item and compare it with every other item. Find all its opportunity costs and find the largest and declare that. And among those, I'll find the smallest. Easy to do, but the problem is it takes n squared time. And because n can be as big as 200,000, n squared is going to give you 4 times 10 to the 10, and this is not something you want to mess with. Okay, it's now going to finish in the time that's allotted to you.
5 seconds.
So n squared algorithm is not a good idea unless you have a really fancy machine.
That's 40 seconds.
Right, something like that. So it all depends on how big your cache is and this and that, but you don't want to get that. It's basically not going to work out for you. That's how they've chosen this number. So the moment you see a number like this, you should know immediately n squared is not the way to go, right? You want to find something small, something better, and that's how we get to range trees. So now we know we want range trees, but we haven't quite figured out the details here. Now, if there are any points here, we don't care because all their contributions are 0. We're only concerned about this. That's the first step. But we are also concerned about things here and here. We're going to ask, among those, how do I figure out the best, right? And so that's where the next problem is. Over on this side, we are interested in, right. So of the things over here, everything contributes their y difference. So among here, I'm just going to find the one with the highest y coordinate, and that's all I care about. Among here, I only care about the one with the highest x coordinate. This also is easy to do because I have my range trees. So I'm going to do the range tree and look at all the x values that are further from here, all the y values that are less than this, and then among that, I'm going to find the largest one. All of this can be easily done from the range trees in log n time, essentially. Okay? So I can find the best guy here. I can find the best guy here. And and I'll keep track of what that opportunity cost was. Is that clear? So that's the opportunity cost for this guy. And I'll do this for everyone. Because there are n of them, and I can do each one in log n time, I have an n log n algorithm. This is 2D. Are you ready for 3D? Questions? This one?
And then that one. And then did you consider everything else, the ones that are bigger?
Yeah, look, over on this side, the x value is smaller, so it's only going to contribute 0, right? And the only thing it contributes is the y difference. So therefore, I pick the one with the highest y coordinate. Over here, it only contributes its x difference, and so I pick the one with the largest x value.
How about the ones that have a bigger x and a bigger y?
Sure, sure. Bigger x than what?
The ones in the red zone.
Yeah.
Yes.
Overall, if this is not empty, I'm not even going to bother with it. It doesn't stand a chance of being the best.
Oh, yes.
Okay. So my first test is this empty? So I'll ask for a count of how many are in this range. Remember, this is like a box now, right? So I'm going to ask, is this box, how many items are in this box? If it says anything more than 0, I'll say, sorry, you're out. I'm going to go look for a better form. Yeah? So I will start to eliminate things in this manner. And if this is empty, then I will look for the best, the farthest on the y here and the farthest on the x here. Whichever is larger, that's the one, that's the opportunity cost for this. And I'll do this for all the phones, and I'll be done eventually because I can find the best. Is that clear? Yeah.
For a phone where that top right region is empty,
Yeah.
you want to find a farthest in the y but less than the x that you
That's right.
chose.
Yeah, that's right.
But the bottom right less than the y but greater
Correct.
than the x. Okay.
Exactly. So each one is a range query. And within that range, I'm going to not count, but I'm going to find the largest guy. That's all easy to do. Cool? OK. So this was 2D. It turns out 3D is pretty straightforward now. I mean, you probably already understand this. So in 3D, I have, instead of just price and performance, I also have this thing called user friendliness, which is just yet another coordinate. I don't care what it's called. So I am going to I'm going to draw this. Oh, yeah. So my 3D drawings are likely to be terrible, so please bear with me. So here is some point in 3D space, right? Here is price, here is performance, and here is, sorry, it's going to be this way. That's user friendliness. Okay. This is not necessarily the origin, but the directions are correct. This is some point, some cell phone. Now, if anything is better in all three categories, it's stupid to even worry about this phone. It's not going to be the minimum, right? So therefore, I'm going to check whether this box is empty. Which box is that? Anything that's higher in performance, higher in price, and higher in user friendliness. Something like that. Are you fine with this? Okay. So I'm going to look at this box that comes out here, and if it's non-empty, done. So it's just a 3D range query. By the way, 3D range trees, what do they look like? Well, it's going to be interesting. I have this basic X tree. From each node, I have this Y tree hanging off of it. Then from each node in the Y tree, there's going to be a Z tree that's hanging off of it. Nasty looking tree. But it's great for searching. Okay? So, if somebody gives you code for it, why not? Just plug it in, right? So here we are. If this box is non-empty, don't bother. If this box is empty, then the box that's symmetrically opposite on the other end and lower, I can ignore it because I don't care how many points are there. I have to look at 6 other boxes, and for each one of them, I have to do some work. So let's look at one of these boxes and see if we understand how to do it. Okay? So let's look at price and performance, but user friendliness is lower. So let's do that one there. Something like that, that box there, yeah? What does this box tell me? These are all points where your current phone has better performance and price, but it's not very good with the user friendliness. So that means the user friendliness coordinate is only going to contribute a 0, right? That clear? So that means only these 2 guys are going to contribute something, and I need to find the one that contributes the most. How do I do this?
Is it going to be the one that's closest to the corner in the back?
I don't know how to look for it. I don't even know how to define it. How do I define it? How do I look for it?
Well, you're saying how we would look for this in the search tree?
Well, okay, let's put the search tree aside. Define it for me, and then I'll tell you how to search for it. Can you define it?
The one that has the one that is farthest away from the one that is relative.
Farthest? What does farthest mean?
So you have X, Y, and Z, right?
Uh-huh.
So you're not considering the Z.
So you're only considering the XY distance.
The X and the Y distance.
But is it Euclidean distance or is it Manhattan distance?
Y2 minus Y1 versus
Right. Okay. Right? Is that clear? You agree with that? So you're looking at the difference in X plus the difference in Y, but not the difference in Z because you don't care about that anymore. It only contributes a 0. And you want to find the best. Now, how do I find that point in the range tree? So here's a trick, which you might like. Let's now go back to 2D. Okay. I have a point here. I have many points. Among these, I have to pick what you said farthest with this new definition of distance. The definition of distance is you add up the X difference and the Y difference. So which of these points are farthest away? Do you know? It's not that clear, is it? Right? So what I do is I draw this 45-degree line and I sweep it. How does that help me? So the 45-degree lines,
Yeah, anywhere on the line the same.
Same distance, right? Because the x distance plus the y distance is the same. Why is that? Because these lines have x plus y equals c. That's the equation of the line. So all those points have the same difference in x and difference in y contribution.
Y equals negative x plus c.
Sure.
So you have the x on the other.
So what I'm going to do is, for each node in my range tree, I'm going to build a new data structure that takes all the x and y coordinates and sorts it by that. And all I have to do is to pick up the best. Does that make sense? Did I lose you? Sorry?
A little bit.
Little bit. All right. So remember how we did range trees in 2D. What did we do? We started with the X range tree, right? So call this the X range tree. Then for every node in the tree, we have this strange Y structure that hangs off of it, right? So we're going to go boom, and we have this Y structure. That helps us look at the Y coordinates of the points that are in here, right? Same points are here, except that here it's sorted by X, here it's sorted by Y. Clear? Instead of sorting by Y, I am now going to sort by X plus Y. Okay. This will help me find the largest y or the smallest y, as the case may be. This will help me find the largest x plus y or the smallest x plus y, as the case may be. I can sort it by whatever value I want, right? If I sort it by x plus y, I can pick anything that's in a certain range in terms of x plus y values. In particular, I can also pick the smallest guy or the largest guy. Perfectly fine. So therefore, this is the structure that I want. Okay? Is this clear? So you have to modify your range tree to have a secondary data structure that's sorted by x plus y. And I will also have another one that's sorted by x plus z, and another by y plus z. I'll have all of these hanging off of each tree, each node. Is that clear? Yeah.
So once to find that
Yeah.
point right there,
Yeah.
We go through the x and then we find it, and then we go through the y, then we
Right.
search through the z.
So I'm going to do this work for every cell phone.
Yeah.
So I go to that cell phone, which is going to be some node in this range tree. That's the guy, let's say. Sorry, it's probably some guy over here, but yeah, it's actually going to be some guy here. Oh, right. So I am interested in everything larger on x and everything larger on y. So it's really not just this, but also everything that's on, right? So it's another way to think about this is, if I come down this tree, every node that I see, I look at the tree that's hanging off of there, and I'll pick that up. So I'm actually going to do this work for every such subtree. So if I show you what to do for one of these subtrees, I'm done, right? So let's focus on one of these subtrees. This corresponds to a certain range in everything that's larger than the x that I have. So this is my cell phone, my phone. It's actually the x value of my phone. And I'm looking at everything to the right of it. I'm going to go to this subtree, right? And I'm going to ask, of the guys here, give me the ones that have larger x plus y values. Okay, so that'll take me to that tree, and I will ask for the right question. That'll tell me, oh yeah, this guy here has the largest x plus y value. Okay, Now, I also have to make sure that the z was smaller, right? So I may have to, so I forgot that step. How do I do this? Right, so, yeah. I will use the range tree to pick up a range of x values, which is the set of x values that I'm searching. For this one, I will go to the z subtree and make sure that I pick everything which has z values smaller than that of my phone, okay, which will give me another subtree there. And within that subtree, I'm going to look for everything that has larger x plus y. Okay, so I kind of rushed it here. I should have first done z. And then for each node here, I have to attach another tree that's sorted by x plus y. I don't know if that made sense. Yeah.
Would the z come off the x or the y subtree?
Z will, you have to build both, it turns out.
With x attached, with z attached to x?
You have to have z attached over here as well, because there are times when you will need to search all. You also have to attach it here because you need, you may need to first search z before you search y, right? So yeah, so that's why the structure needs to be fairly complicated. Okay? It is ugly, yeah. But I'm giving you conceptually how this search happens. The implementation, the engineering part of it, you have to, the code is not easy to write, and there may be efficient ways to write it. But if you understand it conceptually, a lot of things will work out pretty easily. Yes, Paulina?
What do you have to sort all the points? I mean, when you take the highest x plus one.
Right. So the highest x plus y may not be the best. Okay, because the highest x plus y may actually have another point that has x, y, and z well, maybe x and y is lower, but z may be sufficiently large that it doesn't work. Okay.
So just going back a little bit to the 2D problem.
Yeah.
Let's assume we found this center point that we said there's nothing to.
Nothing over here. Yeah.
And you said the bottom right has a property where the
Only the x coordinate is critical.
so the y coordinate is 0.
Y coordinate is not relevant because it contributes 0.
Yeah. So if we found the center coordinate, can we calculate the distance to all the points? And then we know
You could, but that's too much work. There are millions, imagine millions of points here. You only want one guy that has the largest x value in this box. Okay? So you always have to scale this up and imagine that there's a dense cloud here, dense cloud here, dense cloud here, and dense cloud here. If this is not empty, forget it. So you can eliminate lots very, very quickly. Ultimately, you'll get to a bunch of points that have this region empty, this quadrant empty. For those, I'm going to do 2 pieces of work and find the one that's largest. Either they're in this box and have the highest x coordinate, or they're in that box and have the highest y coordinate. Those are the only 2 that can contribute to the largest to the opportunity cost of this guy.
Okay, so that point is not unique. We have
That point is not unique. So I'm going to do this for every point
Gotcha.
for which this square is empty. By the way, if I have points sitting like this, if they are all like this, you'll see that each one of them has the upper right rectangle empty. You see that? So all of those will have to be investigated because they are all candidates for the minimum opportunity cost. All right? And that's what's happening in 3D. In 3D, it's even worse because you will get a lot more points. So even to identify those, you require a range tree because I have to make sure that that entire range is empty. right? Once I do that, I still have to look at the other two quadrants to figure out what is its real opportunity cost. So I look at this quadrant here and figure out which one has the most x coordinate. I'll look over here, figure out the biggest y coordinate. That's the opportunity cost for this. Then I'll go to this and do the same job again. Okay? Right. Questions? So anyway, I don't want to spend more time on this, but I just want you to understand what a range tree is and what it does for you. Pick up the code for it, put it in your package, and maybe try it once and move forward.
For when it's in 3D,
Yeah.
we can think of it as 8 cubes.
That's right. There are eight quadrants,
Yeah.
and two of the quadrants are not particularly useful for you.
Yeah.
One needs to be empty, the other you don't care. The other 6 are all going to contribute something or the other. Okay, so if in this case the x plus y was the important one,
Yeah.
there are others where it's going to be x plus z that's important. In others, there are going to be y plus z that's important. In others, there are going to be only x that's important. Others, it's only y that's important, and so on. So that gives you the 6, and once you do that, you're done. That's why the 8 quadrants came into play for you. So, but in each one, you have to do a range tree query. So just knowing 8 quadrants is not going to help you because you need to know how to deal with each of those quadrants. And that's what I was trying to explain here. All right? Now, by the way, not every competition problem is this difficult, nor is it this hard to code. But, but listen, these are important problems to understand. Once you know what you can do with 3D, think of 1D, because there are going to be there's a good chance that you'll get a 1D range query problem, which is really manageable. So make sure you learn how to do the 1D range query problems, okay? Because that's or a 2D range query problem, because those are quite important. And I wanted you to be comfortable enough with that to say, yeah, I could potentially handle this.
If we could handle the 2D, then we're more or less prepared for the competition?
Well, there is no such thing as more or less prepared, because it's a luck of the draw. You don't know what kind of problems come in. And these guys can crank up the hardness of even a simple 2D query problem and make it horrendously difficult. So I would say don't worry about it. Just think that none of the problems are really undoable. It's possible that you just don't know some domain and there's just no way you're going to answer that without the knowledge. Forget about those, but you need to be sure that conceptually you can solve this problem. Then you just jump in. And my guess is that conceptually you can solve at least, say, 7 or 8 out of 10. Okay, or you have the knowledge for it, you've seen it in some form or the other, or you can potentially work it out. The trick is that time is limited, and even though you could work it out, it may not be workable within a limited amount of time. So that's where you have to kind of make some guesses as to where to invest your time and where not to. So this brings us to strategy for the competition. First thing is make sure that you all have, remember, you can take a folder with printouts of all the code that you want to take. And your folder can be 2 inches thick. Sorry, 1 inch thick. Is it 1 inch or 2? Is it 1 or 2? 2. I think it's 2.
Yeah, I think it's
I'll send you the information just to be sure. And the folder needs to be 1 foot by 1 foot in dimensions, and the thickness can be up to 2 inches, which means you can print out a lot of stuff. Okay. No phones, no electronic stuff. You can't copy and paste anything you like, anything for that matter. Okay, everything has to be typed in. This is why one of your teammates needs to be a really fast typist, if that's possible.
Can you type them in during the period that we're testing out the environment?
Sorry?
Can we type them in during the period that we're testing
Oh
out
yeah,
the environment?
yeah. So you will have a 1 hour period in the morning where you will, everyone will come in, you can play with the environment, you learn what it means to type in a program, run a program, print a program, and so on. So get all those pieces in, figure out how you're going to, what your syntax errors are going to look like, what your runtime errors are going to look like, what an infinite loop looks like, what it means to time out, what it means. You can test all those things. You can see all the error messages. You learn how to submit stuff. All that will be done in the morning. That's why you need pretty much the whole day. Then once you've gotten all that ready, you'll go have lunch, you come back, and you jump straight into the competition. Okay? And the competition is 5 hours. So you would have been well fed by then, but then you will also have enough candy and soda to keep you alive and keep you going. Right? You've done this before. Oh, not in the physical competition environment, right? So, oh no, you were there once, no?
I was involved with Brian.
Yeah, so you were there in that physical thing, yeah. Some other guy, yeah, okay.
Registered participating in
Right.
ICPC competition.
I see. Okay, good. No, so this is quite an excitement. So the other thing to know is that, well, I said this last time. I'll say it one more time. You'll be given 9 to 10 problems. Divide this roughly equally amongst yourselves. In the first 2 minutes, find the easiest problem and solve it. Now, I mentioned this last time. The reason you want to solve the easy problems first is because your score is really a penalty score. And your penalty score is the time it takes to solve your first problem plus the time it takes to solve the second problem, and so on. So the more time you take, the higher your score is. But even if you solve the same set of problems, if 2 of you solve the same set of problems, if you take on the harder problem first and if you take on the easier problems first, who will have the better penalty score? She will have the better penalty score because she solved the easier problems first. Okay? So if this took 3 minutes, if this took 5, this took 100 minutes. And that's the order in which, let's say, she did it. So she would have a penalty score of 108, whereas you do 100 first, and then at 103 you solve the second problem, and at 105 you solve 108 you solve the third problem. What is your penalty score? That's 311. Okay? So clearly you want to solve the easier problems first. Okay? That's your strategy. So your job in those first crucial 15 minutes or half hour is to find all the easy problems and nail them. Yeah. Penalty is all per team. Everything is per team. You're tied to the team at the hip, and everything you all do is going to penalize all of you. Now, if any of your solutions is a wrong solution and it doesn't get accepted, what happens? You get a penalty of 20. So this number goes up. So if one of these solutions was wrong and there was a penalty of 20, this would become 123. Okay? So submitting wrong answers is a bad idea. Submitting wrong answers in the beginning is not it's also not a good idea. So it's almost worth it to spend 1 extra minute or a couple of extra minutes to make sure you're submitting the right thing. Once you figure out the easy problem, and the easy problems are often less than 10 lines of code, and somebody just needs to type in, and it should be sort of obvious how you solve this. So look for those easy problems first. That's your first job in the first 15 minutes to half hour. Okay. If you haven't found any, and if none of your teammates haven't found any easy problems, then there is a problem. Then look at the scoreboard and wait for somebody to solve it. That's what you can do. You'll get clues while you're working on on one of the problems, someone else may have solved a different easy problem. So all these are clues. It'll tell you what to work on next. Now, for once you get past that initial period, in the initial period, your job is simply to go nail the easy problems. And hopefully it's not a lot of programming. It's just small piece of code where there's probably one trick and that's it, or maybe there's no tricks and it's just straightforward. Okay? So between your team members, make sure you talk to each other and decide who's going to be that person who's going to type in first, because you really want somebody who can type in quickly. That's the man in your team. So that's going to be your job. Your job is in the first 5-10 minutes. You're going to have to nail a problem somehow. So in each of your teams, you need to do the same. Find the person who can type quickly. And then type quickly. Well, I should also say type quickly without making lots of typing mistakes, but also debugging quickly. So if the fast typist is not the fast debugger, then get someone else to take over and make sure that problem is submitted. Okay. So that's your first 15 minutes to 30 minute strategy. While one of you, remember there's only one monitor and one computer, so only one person is coding at any given time. What are the other two people doing? Sometimes one person may be looking over the other person's shoulder to make sure they're typing right. This is especially at the start where wrong typing can be quite costly. So you could have one person look over the other person's typing. But a better strategy with strong teams is each one is saying, okay, I'm going to take on problem E, and you say, I'm going to take on problem F, and you work on these two things. How do you work on them? You actually write up pseudocode in hand, by hand, longhand, okay? Yeah?
No.
You're the one who's going to do that?
Yes.
So since there's no other electronic thing, they'll give you enough paper, write things down. Writing down, especially things like here there's a little trick, or here there's a little watch out for this kind of thing. Write all those things down, because whoever is typing it will want to know this. Once you've written something down, go on to you're convinced you've at least got the thing right. If the monitor is still not free, start the next problem, start to think about it. One good idea that some teams use is for each of the problems they write down, oh, this is dynamic programming. Oh, this is graph minimum spanning tree. So that way, whoever takes it on knows that, okay, this is how you're going to approach it. Because often somebody has to debug whatever the heck you write. So that's going to be not so easy if they don't know what it is that you're coding up. Another trick that the fancy UCF team uses all the time is when they get to the harder problems, they type in something and then they send it to the printer and then they sit with it and figure out how to modify it or change it or debug it. That's always a good idea when you get to the harder problems. That's roughly in the second half of the competition. Second half of the competition, you should have printouts of everything that you have partial solutions for. And you will know, okay, this is going to use a range tree or whatever it is, a binary search tree. Code that in, get it in, and start to work on, get some pieces in so that when you actually get the solution, it won't take you too long, okay? There may be pieces that are used in more than one problem, but that doesn't happen very often. You could also share that kind of information. Printing out and debugging is an excellent idea. I definitely recommend this for you guys. That way you will have fewer penalty points because of wrong solutions. When you're sufficiently into the competition, if you're past 2.5, 3 hours, don't worry about wrong solutions. They don't cost you that much. Your aim is to get the thing working. The number of problems is what is key at that time. In the beginning stages, penalties are very expensive. In the later stages, they're not. So focus on getting it done, getting it right, getting it working, rather than on worrying about whether this is right or wrong. Okay? If you think this looks right, I'm not 100% sure, I would say in the latter half, go for it. Don't hesitate. Don't sit on solutions that you haven't submitted. That's a waste, complete waste. Okay? Solutions that are not submitted are never going to be worth anything, whereas solutions that you submit, there is some chance that it may be right. Okay? It is true that we all have incomplete knowledge, so we don't know whether our solution is right or wrong many times. And you experience this. So you have to take some chances, but wait for later to take such chances. There are lots of clues in terms of the time complexity. Use that very liberally. If it says 100,000, 200,000, whatever, immediately n squared is a no-go. If it says 1,000, n cubed is a no-go. Okay? If it says 10 or 15, you know it's going to be an exhaustive search. You know it's going to be an exponential time algorithm. So be prepared for it. So you will get clues. Make sure you use them smartly. And then you will know, okay, this solution should be good enough in terms of the time complexity. Those are all absolute clues for you. Okay? They're not going to tell you, oh, you're going to look for an n log n algorithm. Nobody's going to do that for you. But they'll do that indirectly by giving you the right set of values. Okay? What else can I talk about? So you have a printout. Ricky and Lazaro and Demba have a printout of all the code that they're going to take with them, but it's their code. That's useless for you guys unless you actually try them. So get the electronic versions of this code. At least try it out. Make sure that you know how to run it. Make sure you understand what the input is, what the input format is, and what it means to run them. Then it's worthwhile to put it in your folder. Otherwise, you're going to end up wasting time trying to understand his code, which you did not write and which you did not understand, right? So spend, I would say, at least a few minutes on each of those pieces of code. If you have it, you said you have it in electronic form, right?
Yeah.
And have you already shared it?
It's public. I'm going to share in the server today.
Okay, all right. So on Slack, you mean?
On Discord.
On Discord, okay, yeah. So make sure that you all look at this. You probably have your own code for various things. You probably have some favorite repositories. Go download these. Downloading code is only useful if you have tried it at least once. Otherwise, it's not useful. Okay? Otherwise, it's just obscure code that somebody gave you. I'm not very good at reading other people's code. I'm assuming you don't have that much experience with reading other people's code as well. It's not easy. However, this skill is needed in the competition. Often what will happen is that your partner has typed in something, has this brilliant idea, but the darn thing won't work. And so it's now your job to try and help him or her to figure out how to fix this problem. And that's not easy. I mean, while you are busy working on something else, you would like, this is close, and you could get it done. And so you have to sit and debug other people's programs. When that happens, whoever typed it in, please print it out. In fact, anytime you write up anything, print it out. There are runners who will come and give you the printout, and you can work with this. Fine. So that's the environment you're working with. It's kind of fun. It's really heady. It's very intoxicating, that feeling, but it's worthwhile. I hope you'll learn something.
Just a general question. I saw that FIU is like a center for ICPC competition.
Yeah.
There's other schools coming here.
Yeah. Oh yeah, there are 30 teams coming. Yeah.
Oh, wow.
all the UCF teams are coming here, the 9 or 10 teams. So yeah, we have some serious competition here. But it's the Southeast Regional gets counted all together. So all the 4 sites get counted at the same time.
Southeast, northeast.
Well, Southeast itself has 4 sites, and FIU is one of the 4. And all 4 happen at the same time, and they're graded and scored on the same scoreboard. And I'm going to assume that everyone is in Division 1. Maybe it's just worthwhile for all of you to experience this. Whatever problems you're able to solve, you're able to solve. Just, don't worry about it. I would say you can easily spot the easiest problems. If you're a beginner, you can easily spot the easiest problems because within the first 3, 4, 5 minutes, somebody would have solved something. And those problems are probably easy enough that you can figure out one way or the other. So I would say work on those and make sure, see if you can get those right. That should be your strategy. If you're part of a team where all of you are newcomers, and most of you are, your target should be 2 problems on your own. Okay, and 2 problems in a span of 5 hours is doable. You have all the tools you need. You will have at least 1 hour on the keyboard and the monitor to debug this and to type, debug, and get it right. So I think I'm sure you can do at least 1 or 2. So if you can solve 2 each, your team would have 6 problems. That would easily put you in the top 20, easily. All right. So that's really worthwhile. That's a very respectable showing. Even if you get 2 problems as 3 problems as a team, where each one of you solves 1, I'd say that's a pretty decent showing. Okay. What do you think? Sounds good? Yeah? Michael?
Question, just to double check, it's in PG6, right?
Yes.
Okay, all right.
It's in that big room 116. So each of you will have those big desks and a big monitor, and you'll get locked up for 5 hours with lots of candy and soda. And like, sorry?
If you I am correctly, like in a more advanced division?
Yeah.
Yeah.
You're in Division 1 stuff. You want to yeah. So.
Well, write to me if you really want to be in Division 2. I'll ask what the procedure is. The problem is that if I have people in Division 1 and Division 2, even if you're champions in Division 2, you won't be awarded because FIU as a school has opted for Division 1. Does that make sense?
Yeah, so only if we were to get a
No. All I'm saying is just that you want to win. You're there to win, I assume. And if that's not a major concern for you, then it's fine. Then putting you in Division 2 is okay with me. Sorry?
I'll talk to my team to see what.
Please do. Yeah, please do. The other problem I had was that I could not quite register some of you. I found your names. I added you to the teams, but it still says somehow that you were not added. And let's see, this Chrome refuses to work.